Hello and welcome to my channel. In today's video, we're going to look at some basic concepts about the basic waveforms and how you can create them in the formula controller. So here I have a sine and a square and a saw and a triangle. So yeah, we're going to look at the formulas of how you can create these waveforms and also how you can manipulate some of the attributes of the waveforms like amplitude, phase, frequency, and things like that. So let's get started. So the first waveform that we're going to look at is going to be the sine wave. And the sine wave is made by, surprise, surprise, using the sine function. So yeah, now that my song is playing, this is what the sine function looks like. So let's go over what the sine function is. So in here, I have this website that does a pretty good visualization of how the sine function changes when an angle that you put into the sine function is also changing. So here you can see it says that the sine is the length of the red line, and here you can see inside of the parentheses there's this sine, which is theta, and theta is an angle, which is basically this angle right here. So it's the angle between this line and this line. And now we can see that when the angle changes, the length of the sine is also changing. And then I also have this other visualization which shows the sine function, like the graph, actually being drawn. And you can see now that when this line is changing based on the angle, this is the kind of graph that is going to be drawn when we have -1 and 1 on the y-axis or the vertical axis, and then the angle is in the horizontal axis. In the sine function, you're going to put an angle. So this angle right here between the x-axis and this line here. And what the sine function is going to spit out is going to be a ratio, and that ratio is between the opposite side and the hypotenuse side of a right triangle. Because as you can see, this thing forms a right triangle that kind of has the adjacent and the opposite sides constantly changing. So in other words, the sine function returns this divided by this. And this might be a little bit confusing at first, because you might be like, how can if the sine is the length of this line, how can it also be the ratio of these? And this is just because it's chosen that this circle has a radius of 1. So this line, the hypotenuse line, is always going to be 1. So just think about it. This divided by 1 is always just going to be this, because anything divided by 1 is just going to be itself. So right now, let's just start looking at these different types of variables and what they actually do in this function. So I've got my song playing and I have the A, B, and C incorporated here. So let's start by looking at the A parameter. So when I change the A parameter, you can see the waveform becoming smaller. So the A parameter represents the amplitude of the function. This is the function. This is where the shape is coming from. And when you multiply outside of that, the result is going to be that the shape is going to stay the way that it is, but it's just going to become smaller or larger. So the song time is representing a value that is just constantly increasing at a steady rate. So this is needed because we need to be able to change the output of the sine function somehow. So if I just did a sine function without the song time, I'm just going to cut it out of there. It's just going to return some static value that the sine function would return at this point. As you can see now, if I change B, it's just going to return a static value. But once we put the song time back in, we get movement. So next up, we have the pi function, which in the formula controller returns the value of pi. And what this allows us to do is make the function fit neatly into a pattern length or a song length. So pi represents the length of half a cycle, and in the sine function, half a cycle is basically from this part to this part is a half a cycle. And a full cycle would be from this part to this part. So that's when the function starts repeating in shape. So if I didn't have the pi here, so I'm just going to take the pi out and put the pattern on again. And you can see that the sine just kind of starts off and then the pattern cuts off already. So the function starts again because SongTime is just going forward and now it's 0. Like it just goes forward and jumps to 0, and the sine function doesn't have enough time to cycle through the entire shape of the function. So you could see when I added the pi in, the function got faster. Whatever is inside of the sine function represents the frequency. So I have this b value here multiplied with the SongTime and the pi, and when I change the b value, you can see that the frequency is going to also change. And here we can actually create situations where the sine function doesn't fit into the pattern again because we're multiplying it with this some kind of a weird decimal value. So in order for this function to fit into a pattern, we need to multiply by an integer or maybe some kind of a neat fraction like 0.5, which is half. So in this case, when we're multiplying by half, we get a full graph. And then the final variable that we have here is the C parameter. So what the C parameter is going to do is shift the function up or down. And now you can see that it's actually being cut out of the window because the formula controller window only covers values from 0 to 1. So it's like our sine, technically it still exists above this, but the formula controller output is just unable to show that. So yeah, addition outside of the sine function is going to offset the entire function. It's going to maintain the shape as is, but it just moves it up or down. And I just want to do a little demonstration on a graphing calculator. And here you can also see that if I add a value into this, let's do +5. Now my sine function is all the way up here. Or if I do -5, it's down here. And then for the frequency, I could do 2x. Now it's faster. It's 2 times faster than what it originally was. Or 4x. Now it's 4 times faster. Or I could also do division. I could do x divided by 2. Now it's half as fast as what the original function was. So we actually are lacking one more variable that we could change. So what I'm going to do is change one of these to be a static value. So obviously these don't have to be variables. They can also be static values. So I'm going to do 0.5. So now we have the C parameter free to be used here. So one more thing that you can adjust about this function is the phase offset. So inside of the sine function, we could also do addition. And this is best illustrated by stopping the function, changing the value, and then restarting it, because the phase shift is not that obvious in the formula controller view because of the way that it's moving. Like the view right here is moving. So I'm just going to put the phase shift to +1. I'm actually going to multiply this with 2 times pi, because with 2 pi, we actually get the range for the phase shift to be the size of the entire sine function. So we can set the phase to any point of that kind of up and down curve. Now you can see that it starts by going up and then going down. And if I were to set this to 0.5, we're going to get a sine function going to the opposite direction. So the phase is going to be shifted by this distance. And now we have it start from the bottom approximately, and we change this to be anything. And if I have it at 0, we're adding nothing. So this is going to be the original function. And as you could probably tell from earlier, if I go all the way up to 1, which in this case is 2 pi, because we're multiplying C with 2 times pi, we're going to have the original phase back. So we have gone the full circle of 2 pi. And one more thing that I want to mention is that if we didn't do any of these adjustments, like no amplitude adjustment, no frequency or phase or offset nothing. Like we just have the sine function and SongTime and pi. This is what the sine function will look like. So you're not going to get the entire function to be visible. And this is because the other part of the sine function is on the negative side. It's invisible to the formula controller output because we have no negative values in here. Here in the calculator, you can see the same thing. So the sine function returns a negative value half the time. So, and here in the visualization, it's also obvious because we have this circle that has -1 here on the bottom half. So if you want to make the sine wave be offset correctly and scaled correctly, we need to multiply it by 0.5. And this could also be the variable, so you can change it if you want. But if you don't want to change it and you just want to make a sine that fits into the window, you're going to multiply it by 0.5. So what we have now is a smaller sine that is also halfway in the negative side, but now we have room to offset it, so we can add plus 0.5. So now we lifted it up by 0.5 and now it fits nicely into the window. So another thing that I want to show you is that in the formula controller manual page, which has been updated by yours truly, I've listed some example functions in the bottom here. So here I have multiple examples for the sine function. So we have the basic sine, which I just showed you, which has the multiplication and addition by 0.5. Then we have the adjustable one with the parameters. And then I also have this that has discrete values. So what this is going to do is change the frequency only so that the sine function always fits into the pattern, so it never cuts off. So our next waveform is the square wave. So there are multiple different ways you can create a square, but the way that I often do it is by using the round function and just putting the same sine function that we looked at earlier inside of it. So what the round function will do is always round anything inside of it to the nearest integer. So for the round function, I think if it's equal to 0.5 or less than that, it's going to round to 0, but if it's over 0.5, it's going to round to 1. So this is just going to result in this behavior of the state constantly flipping from 0 to 1, which essentially is the same thing as a square. So for the square, there's also the attribute of pulse width. So the pulse width could be thought of as the length of the up and down state. So I have the A parameter here and I'm adding that into the sine function inside of the round function. So if this were just the sine without the rounding, this would be the offset of the function. And this is going to result in behavior where we can see the pulse width change. And as A increases, the length of the high state also increases, or the length of the low state decreases. So the reason that this happens is that with the A, we're essentially changing the offset of the sine function that is inside of the rounding function, which will kind of change the amount of time that the sine function spends above 0.5. So let's make a little comparison. I'm just going to take this sine out of here so we can kind of look at the function within the rounding function. By the way, Alt and click is how you can open multiple windows in Patcher. I'm just going to copy all these values. So the B one here is the frequency one, just as it is in the sine function. For the most part, this function that is inside here spends above 0.5. So this is why the state of the round function is also mostly at 1. So it just kind of just really quickly goes to 0 when this function goes to its lowest value. If I make A smaller, so let's do something like that, and I'm just going to copy the value and paste it here. You can see that now this function is actually below 0.5 for the most part, so it reflects in the rounding function as well. So, and now you might think, why is this shaped like this? This is not even a sine wave. Well, the frequency is the problem here. So it's so slow that it doesn't have have time to complete the cycle, but I also have another rounding function that is adjusted to work a little bit better. And this is a function that can be found in the manual, so it's the pulse formula. So in this version of the function, the sign is actually halfway into the negative side, but it doesn't really matter as much. Like, the point is that you just need to manipulate the function that is inside of it in a correct way so that it appears to have this pulse width adjustment behavior. As soon as I increase A even a little bit, we get this very fast high state, and it'll keep increasing as I increase A. And now we can also copy the value and look at the function that is inside of the rounding function. So now I can see that our sine is all the way up here this time. And when you look at this carefully, look at the length of the low state now. The low state is the same length as this distance here. So now if I wanted to add some more attributes to the square function, like a frequency, I can just multiply the frequency inside of the sine function, as I kind of mentioned that earlier. And I can add an additional scalar. So if I want to give it more range, I could just add, like, say 2. So now my B knob is technically going from 0 to 2. So now when I change B, you can see that the frequency changes. And the pulse width adjustment is also, like, relative to the frequency. So you can see that the high state actually gets longer as the frequency decreases. So, and now if we wanted to do offset and amplitude, remember that those attributes need to be outside of the function that actually creates the shape, because we want to maintain this shape as it is, but just kind of stretch it or shift it up or down. So here I could do C times this entire thing. So now with C, we can make this function smaller or bigger. And now I'm going to change the C to be addition instead of multiplication. You can do this with either side of the equation. I tend to prefer to do the multiplication first and then addition at the end, but in this case, it doesn't matter. Obviously, there are cases when you're making formulas where you need to remember the order of operations, which is multiplication and division before addition or subtraction, but here it just doesn't matter. So I also added an amplitude scaling, so times 0.5, so it's a little bit easier to see what the offset is doing. So it's the same thing as with the sine. So the next waveform is the saw wave. So the saw wave is also using the SongTime, and it can be manipulated just the same as the other two previous waveforms. So we can change the amplitude and the frequency and the phase and so on. So this is what the saw wave looks like. So the saw wave is created by using the fractional part function. So a fractional part function returns all values that are in between integers. So it's kind of like in the formula controller's case, this will always return the values from 0 to 1. And then when it's at 1, it's gonna jump back to 0 and start over. So it's kind of like it's only giving you values that are decimal values between integers. So when it comes to the SongTime is a value that is constantly increasing. So if we have this, like I'm in the song mode now and I have this longer pattern in there, the song mode will just keep increasing because it's giving you the song position in quarters. So it's just counting quarters upwards over and over until the song jumps back to the start. So if I didn't have this fractional part function here, let's just take it out completely and restart our song. It's just going to be like, bye. It's just increasing, but because the output can't display anything above 1, we can't see it. It's just stuck at 1. So yeah, it'll just depart from Earth and fly into space. So this is why the fractional part function is useful, because it's going to prevent that SongTime from leaving Earth's gravity and flying into space. It's going to drag it down right from where it started. So if you wanted to turn the saw wave the other way around, so it would be decreasing instead of increasing, you could do this. So I'm just going to put the whole thing inside of parentheses to make sure that the order of operations is always correct. So inverting is just subtracting whatever you want to invert from 1. So now I can see that our function has been flipped. So when this part returns 0, the saw wave is supposed to be here. But now when it's being subtracted from 1, what does this entire thing actually return to the output? Well, if this is 0, it's going to be 1 minus 0, which is going to be 1. So the output is actually going to be over here instead of down here. And now just think of all the other values. So let's say that this is going to be 0.75, which is around there. Now we're subtracting 0.75 from 1, and the result is going to be 0.25. So the function is going to be down here. So it just mirrors or flips all the values to be the other way around. Okay, I think that's everything for the saw function. And finally, we have the triangle wave. And I can see that the top of my triangle has actually been sliced off. So again, A for me is usually the multiplier. So A times the function is gonna scale it down. So let's make it a little bit smaller. So the function for the triangle is actually an interesting one. So it's the anti-cosine nested with the cosine. So you might have already looked here when we went over the sine function examples, is that there's also this blue line which says that it's the graph of cosine. And cosine is basically the exact same shape as the sine, but it just has a 90-degree phase difference. And this can be kind of seen here. So at this point, I also want to say that you could do this with sine as well. Like you could do anti-sine and nest a sine inside of it. There's a reason why the cosine is a little bit more convenient, and I'm going to explain it later, but I just wanted to point that out. The anti-cosine is basically just the inverse operation or something that you can use to undo whatever the cosine did. So if cosine takes in an angle and gives you a ratio, then anti-cosine is going to take the ratio and give back the angle. So it's just gonna do the opposite operation. So what is the reason that this makes a triangle? So here we have cosine x. So in here, there would be an angle and it's giving you the ratio. Well, if we have the ratio inside of this, it's going to give back the angle. And these kind of move linearly together because one is always just going to return the other and vice versa. And for a triangle wave, we need linear motion. We need linear motion that increases and then decreases. Okay, now that we got the theory side out of the way, very surprisingly, all the same discoveries that we have made in this video also apply for the triangle wave. So by multiplying outside of this entire function, we can change the amplitude. And by addition, we can change the offset. And by multiplication inside of the inner function, so the inner cosine function, we can change the frequency. So now I want to go over what is the difference between the cosine and the sine in this case. So you can see that our offset is different, first of all. But another thing that is also different is the starting phase. So I needed to offset this by 0.5 to get to the correct starting position. And now you can see that it starts from the midpoint instead of the bottom that the cosine started from. And this is what I mean by the cosine being a more convenient way to do the triangle, is that it starts from the bottom, which is often what you want for a triangle LFO, for example. So yeah, that was the math of basic waveforms explained. I hope you find it useful. I hope that you have a better understanding of manipulating functions now. That's it for this video. Thank you so much for watching. Like this video if you thought it was interesting, and consider subscribing if you're interested in seeing more videos like this one. I will see you in the next one.